The situations that we dealt with yesterday create the need for limits. So the way the limits work is we take a function that gets arbitrarily close to L, which is a limit, as close to L as we like. So it doesn't matter how much or how far away I set my distance to L. If I'm looking at f of x and it's getting arbitrarily close to it or close to that, for all x sufficiently close to x naught, we say that f approaches the limit L as x approaches x naught. And we write it as the limit as x approaches x naught of f of x, or of the function, equals L. And you would read that as the limit of f of x as x approaches x naught is L. Now, this might not make a whole lot of sense to you. We're going to work through these types of problems to get a greater understanding of it. So what we're actually looking at is for what the behavior of a function is near a point. And so if I just try to solve this one, you're going to notice that I have x minus 1 in the denominator. And because that x minus 1 is in the denominator, it means that this function does not exist when x equals 1. So x could not be equal to 1 because I would have 1 minus 1 in the denominator, giving me a 0. So what I need to figure out is how the function behaves near x equals 1. And so if I'm looking at this, I can factor the top out first. It gives me x plus 1 times x minus 1. And so my x minus 1s will cancel out, which tells me that even though it doesn't work for x minus 1, the function near x equals 1 is going to be x plus 1. And if we're looking at when it's around 1, it would be like plugging a 1 into this equation. That gives you 1 plus 1 is 2. If I look at the graph of that, x plus 1 means I start at 1 and go up 1 and over 1 from that point. And then up 1 and over 1 from that point. And so it creates this line. And so when I'm looking at x equals 1, it would be at 2. If I look at the Desmos graph of this original function, looking at the Desmos graph of this, I do x squared minus 1 over, I'll put this in parentheses, over x minus 1 you're going to see it creates this graph of a line that looks a lot like x plus 1. But when I go to actually 1, you see that the point is undefined. There's a hole in this graph where x equals 1. But if I'm looking at the behavior of the graph, it looks just like the line x plus 1. So if I'm looking as it gets closer and closer to x equals 1, what is happening to my y value? The y value just keeps getting closer and closer to 2. It does this if I'm coming from the left, going like that, or if I'm coming to the right, from the right towards the point x equals 1, it also keeps getting closer and closer to 2. So by studying the behavior around the point x equals 1, we can determine or get a good estimate for what the point would be if it did exist at x equals 1. So that's where limits come into play. If I actually try to solve this for x equals 1, it doesn't work. But I can get a good idea of what's happening based on our limit. Just like in the last problem, as we're looking at the limit of that problem, or as we're looking at solving that problem, it was undefined at x equals 1, so it would have a hole. And even though it has a hole there, our limit value does not depend on how the function is defined at that point, x equals 1. So this is our graph. And when I look at it here for this first one, it doesn't matter that my point is undefined. If I'm looking at where it's getting closer to as I approach that point, it's getting closer and closer to 2. So our function is getting closer and closer to 2 as x is getting closer and closer to 1. So our limit as x approaches 1 of our function, x squared minus 1 over x minus 1, is equal to 2 in this case, because it's getting closer and closer to 2. As x gets closer to 1, the y gets closer to 2. If I look at this one, this has a specific defined point using a piecewise function that says as long as x is not equal to 1, we're using this equation. But when x equals 1, it wants you to just have 1. But if I'm looking at the limit, if I was asking what is f of 1, that would tell you it's equal to 1, or this point. But I'm not looking at f of 1 anymore. I'm looking at the limit as x approaches 1 of x squared minus 1 over x minus 1. So I'm looking at the line as it's getting closer and closer to 1. Not 1 exactly, but what's happening as I get close to 1 from both sides. So as x gets close to 1 from both sides, what happens to my y? It's still getting closer and closer to 2. So my answer would be 2 here as well. This third one, if I'm looking at the point where it's getting closer and closer to 1, which is just our function x plus 1. As x gets closer and closer to 1, y still gets closer and closer to 2. So my limit is x approaches 1 of x plus 1 equals 2. So it doesn't matter if the point itself is undefined, if it's defined separately, like in this case, or if it's defined within it. My limit as x gets closer to 1, or as x approaches 1, is still going to be 2 in all three cases here. All right, finding limits by calculating f of x naught. There are still cases where we don't have any restrictions, in which case we just find our value at the point. And so now as I'm looking at these examples, this first one says the limit as x approaches 2 of 4 equals what? Well, for this function, there's no x in here. There's no y. There's nothing. So that tells us this is just a constant function. So it's always 4. So it doesn't matter whether my x is approaching 2, 7, 15. My limit as x approaches 2 of 4 is still going to be 4. Same thing with part B. My limit as x approaches negative 13 of 4 is still 4. It doesn't matter what the x changes to. My graph of f of x equals 4 is just 4. It's a horizontal line at y equals 4. So then if we look at the limit as x approaches 3 of x, x is our function. Now in this case, there's nothing that would stop x as it approaches 3. So if I just plugged a 3 in, it wouldn't give me anything in the denominator that I couldn't divide. So this would just be plugging 3 into the equation. So this would just give us 3. If I look at part D, so the limit is x approaches 2 of 5x minus 3. Again, there's nothing in this denominator that would limit this. There's no square roots. So I can just plug a 2 in. 5 times 2 is 10. 10 minus 3 is 7. That's my limit. And the last one is the limit as x approaches negative 2 of 3x plus 4 over x plus 5. Now because I have a denominator here, an x in the denominator, there is going to be a point where this isn't going to work out, and that would be when it would give us 0 in the denominator. So it would be negative 5 plus 5 equals 0. But this is the limit as x approaches negative 2. So I can just plug that into the value of x and come up with my answer. Three times negative 2 is negative 6. Plus 4 is negative 2. Negative 2 plus, sorry, this is a 5, gives me 3. So my answer is just negative 2/3. All right, that is it for the day. We will pick up where we left off at some point in the near future.